Okay, so let's go on with some more definitions. And let's see what we've got. So let's define a solution. So solutions to a DE, and technically a solution has to always be on some interval. So what I mean by that is I have to have a function y of t if the equation is a differential equation in y, let's say. So a function y of t that is suitably differentiable and that means if it's a first order differential equation, you have to be able to take one derivative. If it's a second order differential equation, you have to be able to take two derivatives. If it's not twice differentiable, it cannot be a solution to a second order differential equation. So a function y of t that is suitably differentiable everywhere on the interval and next part of it satisfies the equation. In other words, if you plug it into the equation, the right hand side does in fact end up being equal to the left hand side. Okay, and now if the function is not differentiable outside the interval that you're focused on, or it doesn't satisfy the equation outside of the interval, that's fine, as long as you're claiming that it's a solution on some particular interval of t, so for some set of t values, then all it needs to be is differentiable on that interval and satisfy the equation on that interval. Okay, so, I should have, let's see here. Let's see. So this is a definition, and I want to make sure, emphasize solutions to a DE on some interval. Okay, that's one definition that we want. Okay, now I'm going to define what an arbitrary constant is. So an arbitrary constant is a constant that does not appear in the statement of a problem in the original DE So for example, when we were talking about objects falling, we had an x double prime equal g. And g is some constant that appears in the differential equation. We don't call that an arbitrary constant. Instead, but it arises while solving the equation. And this is very much like the constant that appears when you take an antiderivative. That was not in the original integral that you were trying to solve, but it arose as you were taking steps through the problem, and you don't know its value. It could be anything. You're allowed to assume it could be 2, 7, 14, e, pi, whatever. Okay, so we call those arbitrary constants. The next definition is a particular solution. And a particular solution is a solution with no arbitrary constants. Oops. All right, and then finally, a general solution. or I should say the general solution to an equation, because there should only be one, the general solution, although it may look like there's more than one, the general solution, because they may have slightly different forms that are equivalent. So this is a solution with one or more arbitrary constants that encompass all possible solutions. Now, how do you know that you've got all possible solutions to a DE? That actually turns out to come down to the question of how many arbitrary constants do you have, and what is the order of a differential equation. A first order differential equation has one derivative, so somewhere in solving it, you'll end up with one integration constant, one arbitrary constant. So if it's a first order equation, one arbitrary constant should be enough. And if it's a second order differential equation, in some equivalent sense, there's sort of two antiderivatives that you have to take in order to solve it, and that means that you should have two arbitrary constants. So that generalizes. Okay, so those are our definitions and of linearity, general solution, particular solution, arbitrary constant, and a solution, just a general notion of solution on an interval. So here I'm going to insert a note about another type of calculation that you're going to have to do. For most of this course, we're going to be talking about actually finding solutions, but until you get a good grip on what it means for something to be a solution, we're going to use the notion of verifying that solution is, or verifying that a particular function is a solution. So what I mean by that is, let's say I give you a differential equation like example y prime plus y equals 0. Now let's say we have no idea how to calculate a solution from this, but somebody says, I think y of t equal 3e to the minus t is a solution. And how do we go about verifying that this is the case? Well, just like we would if somebody says, oh yeah, the solution to that quadratic equation is x equal 4, and you can plug 4 into the equation and see if you get the same thing on the left and right hand side. So this is a fairly simple equation, and we can calculate y prime fairly easily. That's going to be 3e to the minus t. The derivative of e to the whatever is e to the whatever. But then if there's a function up in that whatever, we have to take a derivative by chain rule, and we get a minus sign in front. And then y is just 3e to the minus t. So those two clearly add up to 0. So we have verified that the function proposed is actually a solution to the equation. And so there'll be a few of those questions probably more early in the term, and then we'll start actually calculating solutions. But I want you to keep in mind that anytime you calculate a solution, you should be able to verify that that solution is actually correct, or that the function that you've calculated is actually a solution. Sometimes it'll be a little bit more complicated to do because sometimes the equations are more complicated, so plugging in is messier. But in principle, if you've solved an equation, you should be able to make sure that you got it right by taking your answer and plugging it back into the equation to make sure it's correct. Okay, so I will wrap that up here, and we'll go on to our next set of topics in the next video.